I want you to close your eyes for a second. Picture a dark forest in the middle of summer. It is dead silent. Then you see thousands of fireflies. At first, it is total chaos, just random flashes blinking on and off, no pattern at all. It is just visual noise. But then if you watch long enough, something weird starts to happen.
Right, they start to sync up.
Exactly. A few clusters here, a few there, and suddenly the entire forest is pulsing with light in perfect unison. It goes from chaos to order. It is eerie, and it is beautiful. But here's the question that kept me up last night after reading this research. Is that rhythm, is that synchronization actually the physical definition of a thought?
I mean, that is a massive question, and it is not just about fireflies. It is about how your brain, which is technically just a wet, noisy lump of biology, manages to produce a clear, coherent idea. Today, we are looking at a paper that argues the answer lies in physics, specifically the physics of synchronization.
We are doing a deep dive into a really heavy-hitter paper published in October 2025 by Dan, Ding, and Wu from the University of North Carolina, Chapel Hill. And the title is, well, it is a beast. Explore brain-inspired machine intelligence for connecting dots on graphs through holographic blueprint of oscillatory synchronization.
Yeah, it is quite a mouthful, but if we strip away the academic jargon, the mission here is incredible. We are going to explain in conceivable detail how these researchers are trying to do two things. First, use the math of synchronization to decode the human brain, which they call the hollow brain. And second, use that exact blueprint to reverse engineer a fix for a major fundamental flaw in artificial intelligence, which they call HoloGraph.
So we are jumping from neuroscience to physics and then landing in computer science. And for you listening, we are going to unpack all the dense math and the biological mechanisms. Let us start with the brain. I think most of us have this high school biology idea of neurons. It is a switch, right? Click on, click off. A signal goes from neuron A to neuron B. Very simple.
It is simple, and unfortunately, for the purpose of high-level intelligence, it is mostly wrong, or at least it is way too static. This paper argues that if you look at neurons as just heat switches or static points, you miss the whole picture. Neurons do not just fire, they oscillate, they have a rhythm.
Okay, so instead of a light switch, what should I be picturing?
Think of a metronome or a pendulum. A neuron has a natural rhythm where its voltage swings up and down over time. Now, you have billions of these metronomes in your head. When they are disconnected, it is just noise. It is that chaotic forest of fireflies. But when they interact via lateral connections, when they are placed near each other, they start to push and pull on one another.
And that pushing and pulling is the synchronization.
Right. They align their activity locally to suppress noise. This is the key insight. Synchronization is how the brain actually compresses information. It takes all that scattered, chaotic data and aligns it into a strong, unified signal. That alignment is the thought.
But the paper uses a very specific, almost sci-fi word to describe this blueprint. Holographic. When I hear hologram, I think of, a sci-fi movie or a concert projection. What on earth does a hologram have to do with my neurons?
This is my absolute favorite part of the paper because it connects biology to classical physics. To understand the holographing part, we have to go all the way back to 1801, Thomas Young's double slit experiment.
Oh, I remember this from physics class. You shine a light through two tiny slits in a wall, and on the screen behind it, you do not just get two dots of light, you get a whole series of stripes.
Exactly. You get an interference pattern. Imagine dropping two pebbles into a pond. The ripples spread out. Where the peaks of the two waves meet, they double in height. That is constructive interference. That creates a bright stripe. But where a peak meets a trough, a low point, they cancel each other out. That is destructive interference, which makes a dark stripe.
Okay, ripples in a pond. But you were saying the researchers found these exact stripes inside the human brain.
They did. They took functional MRI data, or fMRI. Now, fMRI usually just measures Boldy signals, blood oxygen level changes, which is pretty sluggish and raw. But they processed it using a very specific advanced tool called a geometric scattering transform, or GST.
Can we pause on the GST for a second? I feel like that is a critical mechanism we should not gloss over. What is the GST actually doing to that raw blood flow data?
Think of the GST like a glass prism. If you shine raw white light into a prism, it breaks it down into a highly detailed rainbow of individual colors and frequencies. The raw fMRI data is like that white light. It's just volume. The GST acts as the prism. It lifts that raw data up into a non-Euclidean space and separates it into individual neural oscillators. It allows us to see the exact rhythm and frequency of the brain regions, not just the volume of blood.
Got it. So the GST turns the brain scan into a map of rhythms. And then what happens?
Then they map how these rhythms interact. They build what is called a cross-frequency coupling matrix, or CFC. Imagine a giant spreadsheet where the rows and columns are different frequencies from different brain regions. When they mapped the correlations, they saw distinct off-diagonal striping patterns in the matrix.
So the data literally looked like the stripes from the double slit experiment.
Precisely. It proves that brain rhythms behave like interfering waves. Your cognitive state is essentially a hologram of synchronized energy. Bright bands of constructive interference and dark bands of destructive cancellation. That is the holobrain.
That is just wild to visualize. But if we want to model this, if we want to actually build a holobrain inside a computer to simulate human intelligence, we need a mathematical equation for it. You cannot just tell a computer to imagine a firefly.
No, you need hard physics. And the paper points to the gold standard for modeling synchronization, the Kuramoto model.
The Kuramoto model. I've heard of this in complex systems theory. It is used for modeling everything from chemical reactions to crowds applauding in a theater.
It is everywhere in nature. Let us break down equation 1 from the paper because this is the absolute engine of the whole concept. It describes how the phase of an oscillator changes over time. The math is d theta over dt equals omega plus the sum of k times the sine of theta j minus theta I.
Okay, let us strip those variables down to plain English for
Yeah.
everyone listening. Let us use the analogy of runners on a circular track. What determines how fast they run, which is that d theta over dt part?
3 things. First, you have omega. That is the natural frequency of an oscillator. In our analogy, that is the runner's personal best pace. If they were totally alone on the track, that is the speed they would naturally go. Every single neuron has its own unique omega.
Everyone has her own inherent pace. What is the second thing?
Next is K, the coupling strength. Think of this as peer pressure. It is how much that runner is paying attention to the neighbor next to them. If K is high, you are obsessed with matching the group. If K is 0, you are in your own world wearing headphones, completely ignoring everyone else.
And the third part, the sine function.
That is the interaction term. The sine of theta j minus theta I. It acts like a magnetic pull based on distance. If your neighbor is slightly ahead of you, this math pulls you forward to catch up. If they are behind you, it drags you back.
So just to lock that in, natural speed plus peer pressure plus that magnetic pull equals synchronization. That is the Kuramoto model.
That is the standard Kuramoto model, yes. But here is the holobrain twist. The researchers realized the standard model was not enough for complex intelligence. The standard model is too simple. Eventually, it just forces every single runner to run at the exact same speed forever. It becomes a mob mentality.
And the brain is definitely not a mob. It has to shift attention constantly. I can focus on your voice, and then I can focus on my coffee cup and then look at the clock. I need selective control.
Exactly. The brain needs a conductor. So the researchers added a completely new variable to the physics equation. They called it YI, or attending memory.
Attending memory. How does that work?
It is a cognitive control mechanism. Think of it like a smart conductor standing in the middle of the running track. The runners are still watching each other, that is the K coupling, but they are also watching the conductor. And this conductor, the YII, remembers the score. It looks at the history of the brain's activity and dynamically adjusts the coupling. It steers the system, deciding what information to sync with and what to ignore.
So the holobrain is not just a synchronized light show. It is a self-conducting orchestra of waves.
That is a beautiful way to put it. And since we are about 5 minutes in, this feels like the perfect moment to do a quick recap of what we have covered so far before we get into the medical cases.
Let us do it. For everyone listening, here are your key takeaways so far. Point 1, neurons are oscillators, not simple switches. They swing like pendulums. Point 2, we use a tool called the geometric scattering transform to pull these rhythmic patterns out of raw fMRI data.
Point 3, when these rhythms interact, they create interference patterns, literal stripes of energy, just like light waves. And point 4, the holobrain models all of this using the physics of the Kuramoto equation, plus that crucial attending memory conductor to steer the synchronization.
Now, I want to ask you listening a question to keep in mind as we move forward. If your thoughts are just synchronization, what happens when that rhythm breaks? Because the researchers did not just leave this as a fun math theory. They applied the holobrain model to real medical data to diagnose diseases.
This is the clinical evidence section, and it is where those abstract stripes become a matter of life and death. They tested holobrain against 3 major neurodegenerative conditions: Alzheimer's disease, Parkinson's disease, and frontotemporal dementia.
They wanted to see if the holographic blueprint looks different in a sick brain. And I'm guessing you can predict the answer here. The interference patterns, those nice, clean, organized stripes in the matrix, they break down, right?
They severely fade out. In a healthy brain, when you look at that cross-frequency coupling matrix, you see strong, clear bands of constructive and destructive interference. The synchronization is tight. But in a diseased brain, the pattern washes out. It becomes blurry and incoherent.
They used a very specific metric to measure this blurriness called sign consistency.
Right. Sign consistency looks at those off-diagonal lines in the matrix. In a healthy brain, the positive and negative phase relationships stay stable over time. The consistency is high. But they found that in diseased brains, this sign consistency drops significantly. They established a diagnostic threshold of 0.5. If the consistency drops below 0.5, it is a very strong mathematical indicator of neuropathology. The orchestra is literally losing the beat.
But the detail that really caught my attention was not just that the rhythm broke down, but where the brain was trying to compensate. The findings on older adults were just fascinating.
This was the major aha moment. They used a massive database called the Human Connectome Project for Aging, or HCPA. They applied holobrain to resting older adults, and they found that the strongest synchronization was not in the memory centers or the advanced logic centers. It was in the left precentral gyrus and the supplementary motor area.
Wait, motor areas, that is movement. Why is an older adult's brain intensely syncing up movement circuits while they were just lying perfectly still inside an MRI machine?
It is a compensatory network. The biological theory is that as the brain ages, standard cognitive processing naturally slows down. The neural wiring gets frayed. So, to compensate and maintain normal reaction times, the brain keeps the motor circuits, the physical engines, revved up and highly synchronized with the visual and attention networks.
So it is kind of like keeping your foot lightly on the gas pedal while you are stopped at a red light, just so you're absolutely ready to go the second it turns green.
Exactly. It is high-idling the engine. The aging brain is working much harder physically just to stay present and reactive mentally.
That is incredibly poignant. And then they compared this to young adults, right?
Yes, using the HCPYA dataset for young adults. And the synchronization blueprint was totally different. In youth, the synchronization was tightest in a loop connecting sensor motor areas to attention, but specifically tailored for fine motor control. So in youth, the default state is readiness for precise, delicate interaction. But in age, the default state shifts to just trying to maintain baseline momentum.
And here's why this matters for the deep dive. Because HoloBrain looks at this underlying mechanism, the actual physical rhythm, rather than just the static roadmap of neural connections. It outperforms standard AI methods in diagnosing these neurodegenerative diseases.
It was far more accurate. Because standard diagnostic AI looks at the map of the roads. HoloBrain is looking at the flow of the traffic.
Okay, so we have firmly established that the physics of synchronization can decode the human brain. Now, the paper takes a massive pivot. It flips the script. Can we take this biological brain mechanism and use it to fix artificial intelligence? This brings us to the second half of the mission, HoloGraph.
To understand why HoloGraph is such a big deal, we have to look at why current AI is hitting a brick wall. Specifically, we are talking about graph neural networks, or GNNs.
GNNs are the AI models we use to understand any data that looks like a web. Social networks, citation maps, molecular structures, fraud detection rings.
Correct. And right now, the mathematical engine powering almost all traditional GNNs is based on a concept called heat diffusion. The equation is the partial derivative of x with respect to time plus the Laplacian of x equals 0.
Whoa. Okay, let us translate that partial derivative into a visual analogy for our listeners. What is heat diffusion in a network?
Imagine a radiator warming up a cold room. Or even better, imagine dropping a single drop of dark blue dye into a glass of clear water. If you want to share information between nodes in an AI graph, let us say you and your friends in a social network, the AI lets your data diffuse like that dye. It spreads from your node to your friends and then to their friends, smoothing everything out.
I see the immediate problem there. If you let that blue dye sit in the water for too long or you stir it too much,
the whole glass just turns a muddy, uniform light blue. Everything looks exactly the same. In AI, this catastrophic failure is called oversmoothing. If you make the neural network too deep, trying to learn complex, distant relationships across the web, all the nodes become indistinguishable. The AI literally loses the ability to tell you apart from your next-door neighbor.
So in current AI, diffusion equals blurring. And the UNC researchers looked at this and said, let us stop using heat. Let us use the Kuramoto model instead.
Enter HoloGraph. Instead of a drop of dye spreading out and diluting, I want you to imagine every single person in that social network is a runner on a spherical track. You are an oscillator.
Okay, I am on the track. I am a node.
The AI connects you to your friends, but instead of your data bleeding into theirs like wet paint, you interact via synchronization. You adjust your phase to match your friends. You form a synchronized cluster.
We are running in a tight pack.
You are in a pack. And this is the absolutely critical mathematical difference, because you are oscillating, you maintain your distinct identity, you are running with the group, but you have not melted into the group. You still have your own individual phase angle on that sphere.
Wow. So you can have multiple groups running on the exact same track at different phases without them ever merging into a single muddy blob. That completely solves the oversmoothing problem.
It solves it perfectly. You can make the AI network as deep as you want, and the signal stays crisp because it is a rhythm, not a dilution. But HoloGraph also solves an even trickier problem in machine learning: heterophily.
Heterophily, that is the scientific term for opposites attract, right?
Yes. Standard AI diffusion relies heavily on homophily. The assumption that connected nodes are very similar. You are friends with people who like the same movies as you. But what about a predator-prey graph in an ecosystem? A wolf node is connected to a rabbit node, but they are definitely not similar. Or think of a dating app algorithm. You might be explicitly searching for someone with completely different traits than you have.
And standard heat diffusion fails there because it tries to mathematically average out the wolf and the rabbit into the exact same muddy color.
Exactly. It forces them to blend. But HoloGraph handles heterophily beautifully because of its coupling dynamics. The synchronization equation allows for incredibly complex relationships. You can be strongly coupled to someone, but maintain a distinct phase difference. You can literally run exactly opposite to them on the track, completely anti-synchronized, yet still be perfectly linked by the shared rhythm.
And the researchers proved this works, right? They tested HoloGraph on some notoriously difficult benchmark data sets. I think the paper mentioned the Texas, Wisconsin, and squirrel data sets.
They did. For context, those are web page networks where pages frequently link to completely dissimilar categories. They are highly heterophilic. Standard GNNs usually fail hard and crash on these. But HoloGraph achieved competitive and, in many cases, the absolute best performance across the board because it allows nodes to dance together dynamically without stepping on each other's toes.
We are about 12 minutes in now, and we have covered a massive amount of ground. Let us do our second recap to make sure this all sinks in for you listening.
Sounds good. Here are the core takeaways for the AI side. The problem is that traditional AI uses heat diffusion, which leads to oversmoothing. Everything blends into a muddy mess. The solution is HoloGraph, which replaces diffusion with oscillatory synchronization.
And the visualization to remember is that data points act like runners on a sphere. They group together by syncing their speed, which preserves their individual identity even in super deep networks. And finally, this handles heterophily, or opposites attract, in a way standard AI simply cannot.
Perfect. Now, I want to move to what I consider the deepest dive aspect of this entire paper, because the implications here go way beyond just getting better scores on a data set. It implies that by using this physics-based approach, the AI can actually learn the rules of the road without ever being given a map.
You're talking about the unsupervised learning experiment they ran.
Exactly. They took the HoloBrain model and fed it raw fMRI data. But they did not tell the AI which brain regions were which. They stripped away all the labels. They just let the Kuramoto physics run wild to see what would naturally happen.
They just let the oscillators interact. And what did they find?
The model spontaneously rediscovered the brain's canonical subnetworks. Without any human prompting, it identified the default mode network, which handles daydreaming and internal thought. It found the visual network, the attention network, all purely on its own.
It uncovered the natural biological organization of the brain just by listening to the rhythm. That is incredible.
It is profound because it suggests the model is not just memorizing statistical correlations, which is what 99% of current AI does. It is actively uncovering the dynamic reasoning of the system.
I really want to highlight that distinction for our listeners. Statistical correlation versus dynamic reasoning. That feels like the absolute core thesis of this whole paper.
It really is. Current AI is a master of brute force statistics. It knows that if A happens, B usually follows. But it does not actually understand the mechanism. It does not know why. HoloGraph is trying to build a new generation of AI that thinks in rhythms, interactions, and causal physics. It creates a system that is robust because it understands the actual physics of the interaction, not just the probability of the outcome.
It creates an AI that generates holographic interference patterns.
Yeah.
Just like we do.
Just like us. It bridges the gap between the machine mind and the human mind.
So we have gone from fireflies To brainwaves, to disease diagnosis, to fixing the fundamental flaw in graph neural networks, this is a massive synthesis of ideas. Let's bring it all home. If you had to summarize this entire Holo framework in a nutshell, how does the whole pipeline flow?
It is a elegant four-step loop. Step one is input. You take the raw data, whether it is a brain scan or a massive social graph, and you use the geometric scattering transform to turn it into oscillators. You give the data heartbeat.
Step two is process. You let the Kuramoto dynamics take over. The nodes synchronize based on their natural frequency and how strongly they are connected.
Step three is control. You add the attending memory. That is your conductor. It steers the system based on history so it does not just crash into a uniform mob.
And step four is output. You get interference patterns, complex stripes of synchronization that encode high-level information, whether that is a diagnosis of Alzheimer's disease or accurately classifying a tricky node in a dataset. Nature inspired the math decoded the brain, and then the brain inspired the AI. It's a beautiful cycle.
It is. And honestly, it leaves us with a very provocative thought about our own minds, which I think is a great way to wrap this up.
What is that?
Well, we talked about how a clear, focused thought is a stable interference pattern, constructive interference, bright, strong stripes in the matrix. But what about a conflicted thought? What happens physically when you are torn between two difficult choices?
Wait, is a conflicted thought just destructive interference?
Yeah, it very well might be. In the CFC matrix, that conflict would show up as the dark bands. Or perhaps it is two competing synchronization clusters on the sphere, fighting for dominance, unable to resolve into a single phase. If our consciousness is just the geometry of synchronization, then confusion is not just a psychological feeling, it is literally a mathematical cancellation of physical waves.
That is heavy. It completely redefines what it means to make up your mind. It is literally about forcing your neural oscillators to align into a single coherent phase.
It gives a very literal scientific meaning to the phrase, getting on the same wavelength.
I love that. I want to leave you listening with a challenge today, a way to visualize this deep dive in your own life. Wherever you are right now, just close your eyes for a second. Imagine your thoughts not as words in your head, but as ripples in a pond. When two ripples meet, they make a pattern, and that pattern is your thought.
And here is a question for you to chew on based on the clinical data. We learned that aging brains automatically increase synchronization in their motor areas. They rev the physical engine to compensate for mental decline. If you could voluntarily synchronize one specific part of your brain right now to boost your daily performance, which region would you choose?
That is a great question. Would you sync up your visual cortex to see more detail in your work, your auditory cortex to be a better listener, or maybe your prefrontal cortex for pure, unfiltered focus?
Personally, I would sync my fine motor cortex. I would love to finally be able to play the piano properly without my hands getting confused.
And for the techies and developers out there, next time you look at a social network or a complex data set, stop thinking about static links and lines. Think of oscillators. Think of runners on a track. Ask yourself, are you actually syncing with your network, or are you just diffusing into the background noise?
Exactly. Do not let yourself be oversmoothed. Maintain your phase.
Keep your identity. Stay synchronized, everyone. Thank you for surviving the density of the Kuramoto model with us today. This has been a deep dive into the fascinating worlds of holobrain and holograph.
It has been an absolute pleasure.
We will see you on the next deep dive.